Welcome to all. In the last classes, we have seen the various types of instruments used for measuring AC and DC voltages. In that we have seen permanent magnet moving coil type instrument, which is used for DC measurement, and moving iron type instruments, which is used for AC measurement. If the permanent magnet moving coil instrument is used for AC measurement, means what will happen? Why can't we use permanent magnet moving coil type instrument for AC measurement? If you give AC supply to a permanent magnet moving coil type instrument, means what happen? Because of the alternating quantity, an alternating torque will be developed in that permanent magnet moving coil type instrument, which will make the deflecting torque or the moving system will move rapidly, so that the pointer cannot follow the rapidly changing alternating torque which is developed in the instrument. So the pointer will not show the perfect deflection which is to be measured. So we cannot use permanent magnet moving coil type instrument for AC measurement. So if you want a instrument to measure the AC quantities, means what you need is the magnetic field produced in that instrument must also change along with the change in current. So this is a basic principle used in electrodynamometer type instruments. Next we are going to see the instrument which is used to measure power. So far we have seen AC and DC voltmeters and ammeters, which is used to measure AC and DC voltage and current. So in case of DC circuit, if you want to measure power, means we can measure current and voltage independently, and by the product of voltage and current we can obtain the power. But in case of AC circuits, if you want to measure power directly, means we have to use wattmeter. So the necessity of wattmeter is to measure power in AC circuits. So in this class we are going to see wattmeter, what are the types of wattmeter, and the construction and working of wattmeter. So in this class we are going to see electrodynamometer type wattmeter. First we will see what is wattmeter. A wattmeter is a device which is used to measure power. What is power? Rate at which the energy is transferred is called as power. Rate at which the energy is transferred is called as power. So in case of DC circuit, we can measure power with the help of voltmeter and ammeter. From that voltmeter and ammeter we can measure the DC voltage and current. So from that we can measure power or calculate power by using the voltage and current. If this is also can be written as V square by R, which is equal to I square by R, if the values of resistance are known. But in case of AC circuit, the instantaneous value of power will be given, which is equal to P is equal to V into I, where V is the instantaneous value of voltage, I is the instantaneous value of power, and P is the instantaneous value of power, V is the instantaneous value of voltage, and I is the instantaneous value of current. So both the voltage and current waves are sinusoidal. So the current lags the voltage by an angle phi. So by substituting the values of instantaneous values of voltage and current in this equation, we will get the average power over a cycle as capital P, which is equal to Vi cos phi, where V and I are the RMS value of voltage and current, and cos phi is the power factor. So in case of AC power measurement, this power factor comes into picture for calculating the average power. So for measuring this average power in case of AC circuit, we are using wattmeter. Now let us see what is wattmeter. So wattmeter is nothing but it is a combination of ammeter and voltmeter. It has both current coils and pressure coils. The principle of wattmeter is the operating torque for this wattmeter is produced due to the deflection of or due to the interaction of fluxes produced in the fixed and moving coil. Due to the interaction of two fluxes produced by the fixed coil and moving coil, the operating torque will be produced in case of wattmeter. Let us see the types of wattmeter. We have three types of wattmeters. One is electrodynamometer type wattmeter. Second one, induction type wattmeter. And third one, electrostatic wattmeter. So, we are going to see the first one, electrodynamometer type wattmeter. First, let us see the construction of electrodynamometer type wattmeter. So, the electrodynamometer type wattmeter has two coils. First one is the fixed coil. So, the fixed coil is divided into two halves. The fixed coil is divided into two halves. In between the fixed coil, a moving coil will be placed with the help of a spindle arrangement. So, here in the center of the fixed coil, the moving coil will be placed. To the common spindle, a pointer will be connected, which will move over the graduator scale. So, this one is the pointer. This is the cross-sectional view of single phase electrodynamometer type wattmeter. Now, we are seeing single phase electrodynamometer type wattmeter. Here we are having two fixed coils. That is, fixed coil is divided into two halves, and a moving coil which will be placed in the center of the fixed coil, which is connected to the spindle. To the same spindle, we have a pointer which moves over the graduator scale. Let us see the connection of wattmeter to measure power. How we can connect wattmeter in order to measure power? Let us draw the equivalent circuit. You know that the fixed coil which is divided into two halves, and there will be a moving coil which is connected between this fixed coil, and a resistor will be connected in series with this fixed coil. The supply voltage is given here, just nothing but the will represent moving coil as fixed coil as Fc and moving coil as Mc. There will be a spindle arrangement. To the spindle, a pointer will be connected. So, the pointer will move over the scale. So, this one is called series resistor, and it will be connected to the load. First, let us see what are all the parts in a single phase electrodynamometer type wattmeter. First one is fixed coil. So, this fixed coil is also called as field coil. It is used to produce the necessary field, or it can also be called as current coil. Generally, we represent as CC, that is current coil. So, this fixed coil will be a varnished air core coil and will be circular in shape. As we have seen in the diagram, this fixed coil will be divided into two halves. So, why it is divided into two halves is in order to produce uniform field near the center of the coil, because near the center of the coil, it is in the center of the fixed coil, moving coil will be placed. So, in order to produce uniform field near the center of the coil, this fixed coil is divided into two halves and it carries the massive current in the circuit, carries a large amount of current which is to be measured in the circuit and will produce the necessary magnetic field. This fixed coil will always be connected in series with the load. Next one is moving coil. This moving coil is also called as voltage coil or pressure coil, normally represented as PC. This moving coil will be wound either as self-sustaining coil or wound on a aluminium former, as in the case of permanent magnet moving coil type instrument. If aluminium former is used, then eddy currents will be induced which causes errors in the system. So, the thickness of the aluminium former is made as light as possible in order to reduce the eddy current. This moving coil will be mounted on the spindle which is free to move in the center of the fixed coil. It is always connected across the supply voltage. So, this moving coil can be either a self-sustaining coil or it can be wound on aluminium former, as in the case of permanent magnet moving coil type instrument. If the aluminium former is used, means it must be as light as possible in order to reduce the eddy current which is produced in that aluminium former, which affects the deflecting torque, and this moving coil will be mounted on the spindle which is placed in the center, and this moving coil will be always connected across the supply voltage. So, third one is control springs. As already we have seen in moving coil and moving iron type instrument, this controlling springs are used to produce the controlling torque. You know that the controlling torque is used to make the pointer to come to rest at a steady state position when there is current flowing in the coil. If the current flowing through the coil is removed, the pointer must come back to the zero position. So, this controlling torque will make the pointer to come back to zero position when the current supplied to the coil is removed. Next one, damping system. As in the case of moving iron instrument, here air friction damping is used to produce the damping torque. What is the use of damping torque? The damping torque is used to reduce the oscillation of the pointer, so that the time taken for taking the readings will be reduced, so that the pointer will also come to rest at a steady state position. Okay. Why not eddy current damping is used in case of wattmeter? Here we have used coil to produce necessary magnetic field. So, the magnetic field produced by the coil will depend upon the amount of current flowing through the coil, which is very weak. But in case of permanent magnet moving coil type instrument, we have used permanent magnet in order to produce the necessary magnetic field. So, we cannot use eddy current damping for wattmeters used to measure AC quantities. So, the fifth one is pointer. So, pointer is used to show the amount of power transferred to the system. So, the pointer along with this pointer moves over graduated scale, and there will be a mirror arrangement to measure power without any parallax error. Parallax error is nothing but, as we have already discussed, it is the error occurring while taking readings. Next, we will see the operation of, let us see the operation of wattmeters. What happens? We have two coils, one is fixed coil, another one is the moving coil. When current passes through both fixed coil and moving coil, a magnetic field will be produced in both the coils. So, the field produced by fixed coil will be proportional to the load current, and the field produced by moving coil will be proportional to the supply voltage. So, strength of the field produced by these coils depends upon the amount of current flowing through them. So, the deflection torque will be produced because of interaction of these two fluxes produced in each coils. So, the deflection torque produced is given by the power supplied to the load. So, the deflection torque produced will be directly proportional to the power supplied to the load. So, we can say that the deflection torque TD is directly proportional to the current through the current coil or the fixed coil, which is proportional to the current through the pressure coil or voltage coil IPC, which is proportional to IV by R, that is the total voltage and current through the circuit divided by the series resistance. So, in DC circuits, the deflection torque produced will be directly proportional to the power, which is given by V into I. But in case of AC circuits, the instantaneous torque will be produced, which is represented as TI, instantaneous torque, which is proportional to instantaneous power. Due to moment of inertia of the moving system, what happens? This deflection produced will be directly proportional to the average torque on the system, which is proportional to the average power. So, in case of AC circuits, the deflection torque TD produced will be directly proportional to the average power transferred to the load, which is VI cos phi. Next, we will see the effect of mutual inductance of the fixed and moving coil on the deflection torque TD. What is the effect of mutual inductance on the deflection torque TD? So, the mutual inductance between the fixed and the moving coil varies as the moving coil moves because of the deflection torque produced. So, what happens because of this mutual inductance? The deflection torque is affected. So, let us draw the equivalent circuit of wattmeter, fixed coil, moving coil with the series resistor, which is connected to the load, supply voltage VPC. So, the total current is taken as I. IC is the current through the current coil or fixed coil. So, let us see moving coil, current through moving coil is taken as It is also called as pressure coil, so IPC. This one is the series resistance R. So the terminal here will be marked as M, that is it is connected to the main. Here it is connected to the load. That is a common terminal for current coil and moving coil, that is voltage coil. So voltage terminal. So the power supplied to the load will be given as W is equal to VPC, which is the voltage across this moving coil, into current flowing through this current coil, to the cos of angle between this voltage coil and current coil. Let me draw the equivalent circuit for electrodynamometer type wattmeter. Let we consider I1 and I2 as the instantaneous value of current in fixed coil and moving coil. L1 and L2 are the self-inductance in fixed coil and moving coil, and M is the mutual inductance between the coils. So the fixed coil, the current through the fixed coil is taken as I1, the self-inductance value of the fixed coil is taken as L1, and the moving coil, the self-inductance is taken as L2, and the current through this moving coil is taken as I2. The EMF induced in coil fixed coil is taken as E1, and the EMF induced in moving coil is taken as E2, and there will be a mutual inductance M between these two coils. So what is the value of flux linkage in coil 1? So the flux linkage in coil 1 is taken as phi 1, which is equal to L1 into I1 plus M into I2. The flux produced because of the EMF induced in this first coil, and also the flux linked with the first coil because of current flowing through the second coil is taken as I2. This is the flux linkage in coil 1. Next, what is the value of flux linkage in coil 2? Taken as phi 2, which is equal to L2 I2 plus M into I1. The flux linkage in coil 2, and the flux which is produced in the first coil, which is linked with the second coil, is M into I1. Let me take this equation as equation number 1, this as equation number 2. We know that the EMF induced in first and second coil is the rate of change of flux linked with each coil. So EMF induced in first coil E1 is taken as d phi 1 by dt, and in second coil E2 is taken as d phi 2 by dt. Let me take this as equation number 3. So the total electrical input energy is equal to the EMF induced in first coil and current flowing through the first coil plus the EMF induced in the second coil and the current flowing through the second coil. So the energy in first and the second coil. So from equation 3 we can rewrite this equation as I1 into d phi 1 plus I2 into d phi 2. So from equation 3 we know that E1 into dt is equal to d phi 1, E2 into dt is equal to d phi 2. So by substituting the values of I1, phi 1 and phi 2 from equation 1 and 2, so substituting 1 and 2, this equation, we will get I1 d of L1 I1 plus m into I2 plus I2 into d of L2 I2 plus m into I1. So, differentiating this equation, we will get I1 square dL1 plus I1 L1 dI1 plus I1 I2 dm plus I1 m into dI2 plus I2 square dL2 plus I2 L2 into dI2 plus I1 I2 dm plus I2 square m into dI1. So, I have differentiated all these terms. So, let me take this equation as equation number 4, which is the electrical input energy. So, the electrical input energy is given by this equation. So, the energy stored in magnetic field due to the self inductances L1, L2 and mutual inductance is given by, the energy stored is given by, energy stored is equal to half L1 I1 square due to self inductance L1, half L2 I2 square, which is due to the self inductance L2 plus I1 I2 into m, this is due to the mutual inductance. So, now I have to find the change in stored energy. Which is d of half L1 I1 square plus half L2 I2 square plus I1 I2 into m. So, by differentiating this equation, we will get I1 L1 dI1 plus half I1 square dL1 plus half I2 square dL2 plus I2 L2 into dI2 plus I1 m dI2 plus I2 m dI1 plus I1 I2 into dm. Let me take this as equation number 5. So, we have calculated the electrical input energy and energy stored, change in energy stored. So, by the principle of conservation of energy, the electrical energy input is given by the energy stored in the system plus the mechanical energy. The mechanical energy is the energy used to do useful work. So, by rearranging this equation, we will get mechanical energy or mechanical work done is equal to energy input minus the energy stored. So, from equation 4 and 5, the mechanical energy is given by, so the common terms in equation 4 and 5 will get cancelled, so that we will get half I1 square dL1 plus half I2 square dL2 plus I1 I2 into dm. Since L1 and L2 are constants, the rate of change of self inductance dL1 and dL2 will be 0. Therefore, the mechanical energy is given by I1 I2 into dm. Let me take this equation as equation number 6. Let me take Ti as the instantaneous value of deflection torque Td and d theta be the change in deflection. So the mechanical energy is given by, mechanical energy is nothing but the mechanical work done by the system is given by Ti into d theta. So we know that Ti is instantaneous value of torque into d theta is given by substituting the mechanical energy value from equation 6, which is equal to I1 I2 into dm. This is from equation number 6. So if we calculate value of Ti is equal to I1 I2 into dm by d theta. So value of instantaneous value of deflection torque. Let me take this equation as equation number 7. So in case of AC operation, the total deflection torque Td over a cycle can be obtained by integrating the value of instantaneous torque. So the average deflection torque over a cycle is given by 1 by T integral 0 to T Ti into dt. Substituting the value of Ti, Td will be equal to 1 by T integral 0 to T I1 I2 into dm by d theta into dt. Since dm by d theta is constant, Td will be equal to dm by d theta 1 by T integral 0 to T I1 I2 into dt. Let me take this as equation number 8. Since the two currents I1 and I2 which is produced in the fixed coil and moving coil are sinusoidal, it is displaced by an angle phi. So the instantaneous values of current can be written as I1 is equal to Im1 into sin omega t, I2 is equal to Im2 into sin omega t minus phi. Let me take this as equation number 9 and 10. So substituting 9 and 10 in 8, get Td equal to dm by d theta 1 by T integral 0 to T Im1 sin omega t into Im2 sin omega t minus phi into dt. So by integrating this equation, we will get deflecting torque Td as I1 I2 cos phi into dm by d theta. Here I1 and I2 are the RMS value of current in fixed coil and moving coil. So now we have derived the equation for deflecting torque in wattmeter. We know that the controlling torque Tc is produced with the help of the spring, which is directly proportional to the deflection of the pointer. So Tc will be equal to K into theta. So at steady state, the deflection torque produced will be equal to the controlling torque Tc. So I1 I2 cos phi dm by d theta will be equal to K into theta. By rearranging the equation, the deflection theta can be written as I1 I2 by K cos phi dm by d theta. Here I1 is the current flowing in the current coil or fixed coil, I2 is the current flowing in the pressure coil or voltage coil, that is moving coil. So instead of I2, since I2 which is the current in pressure coil, so this I2 can be written as VPC, which is the voltage across the pressure coil divided by the series resistance value R. So if you substitute the value in equation 9, theta will be equal to VPC I1 by KR cos phi dm by d theta. So, replacing all these constants with a common constant. So, theta will be equal to k1 VPC I1 cos phi, where k1 is taken as 1 by k into r dm by d theta. So, we know that VPC I1 cos phi is nothing but the power in the wattmeter. So, theta will be equal to constant into the power. So, we can say that the reflection produced by the wattmeter will be directly proportional to the power consumed. So, the reflection will be directly proportional to the power in case of wattmeter. Now, let us see the advantages of single phase electrodynamometer type wattmeter. It has uniform scale because the reflection torque will be directly proportional to the true power. And also we have used spring control for producing the controlling torque. The scale will be uniform in case of electrodynamometer type wattmeter. Second one is it has higher accuracy, and third one, the power consumed will be low. It is free from hysteresis and eddy current errors because we have used the coil which are air cooled, so that the hysteresis and eddy currents are reduced. Next we will see the disadvantages. So, it can be easily affected by stray magnetic fields because the magnetic field is produced by this coil which is very weak. So, it can be easily affected by the external magnetic field which will affect the deflection torque produced. So, to eliminate this stray, prevent this instrument from the stray magnetic field, the instrument should be shielded. Next, the error due to mutual inductance between the coils will affect the deflection torque produced. We have seen that the deflection torque produced will get affected because of the mutual inductance between the fixed coil and the moving coil. The third one is this expensive because of the construction, and it also requires more operating current due to weak magnetic field which is produced by the coil. So, the operating current required is more. Now, let us see what are the types of errors in the single phase electrodynamometer type instrument. The first one is eddy current error. As we have already seen, this eddy current errors occurs in the metal parts of the instrument. So, because of this eddy current induced in the metal parts of the instrument, what happens? This eddy current will interact with the current which is to be measured, which changes the deflection torque. So, this eddy current will interact with the instrument current and it will change the deflection torque, which causes errors in the measurement. So, how we can eliminate this eddy current is the metal parts used must be kept minimized and it should have high resistivity, so that the error due to eddy current can be reduced. Second one is stray magnetic field error. We know that here the operating field is produced by the coils, which is very weak since we have not used any permanent magnet to produce the field. Here the operating field is very weak, so this operating field can be easily affected by the external stray magnetic fields, which will causes error in the system. So in order to eliminate this stray magnetic field error, what we have to do is we have to shield the instrument with an iron case so that the external magnetic field will not affect the operating field of the instrument. So next one is the temperature error. This temperature error is caused by the self-heating of the coil. Since we have fixed coils and moving coils, due to the self-heating of the coil, temperature error occurs because there will be a change in resistance of the coil gets heated. The coil gets heated means there will be change in the resistance of the coil, so temperature error occurs. So in order to eliminate this temperature error, we have to use temperature compensating resistors along with the moving coil in order to eliminate the temperature errors. Next one is the torque to weight ratio errors, which causes friction errors. So in order to have a required deflecting torque, what we need is the MMF of the moving coil must be large in order to produce the required deflection torque. We know that the MMF, the magnetic motive force, is equal to the number of turns of the coil and the current flowing through the coil. So if you want to increase the magnetic motive force, means what we have to do, either we have to increase the number of turns of the coil or have to increase the current flowing through the coil. If the current flowing through the coil is increased, what happens? It causes the heating of springs. Since the current passes through the coil, also passes through the springs, which is used for controlling torque, this causes the heating of the springs. So we cannot increase the value of current. So only option is we have to increase the number of turns of the coil. So if you increase the number of turns of the coil, what happens is the weight of the coil is increased, the total system weight will be increased. So what happens? The torque to weight ratio is decreased. So this causes frictional errors. These are all the various types of errors occurring in a single phase electrodynamometer type wattmeter. Thank you.